So this is a little bit of review. We talked about some vocab words that involve circles in a previous section. But just as a reminder, a chord is a segment with endpoints on the circle. Okay, so it doesn't have arrows on the ends. If it did have arrows, what would that be called?
Lines.
Yeah, secant. Okay, so a secant is a line that goes through a circle. A chord has endpoints right on the circle it stops. Okay, so let's ask these two questions. Is a diameter considered a chord?
Yeah.
Look at the definition of what a chord is.
Yeah.
So is a diameter a chord? Yes. Okay, is a radius a chord? Why? Where's one of the endpoints? On the center, which is not on the circle. Okay. So we're going to be looking at different properties of chords within circles, when they're equal, when they're not equal. But here's kind of the main idea we're looking at today. Congruent chords have congruent arcs, and congruent arcs have congruent chords. What I mean by that is if you have two chords that are the same length as each other in a circle, the chords that are open up to them are also going to be the same length. Okay, so those chords there are going to have the same measure and the same length. And vice versa. If they tell you the chords are the same, then the arcs are the same, and if the arcs are the same, the chords are the same. Okay, a diameter that is perpendicular to a chord bisects the chord and the arc. So if there's a diameter, they're going to tell you it's a diameter by actually posting the center on it. That way you know it's actually going right through the center of the circle. So if this is a diameter right here, and it's perpendicular to a chord, a couple of things happen. Like it says in this sentence right here, the chord gets cut in half, and the arc it's open to also gets cut in half. So if there's algebra on here, which you can guarantee you're going to see in the homework and also on the test, if there's a diameter and it's perpendicular, if there was a 3x here and a 4x plus 7, you're going to set them equal to each other. Okay? Questions? So as you're looking back at your notes, it would probably be wise we should do this. That's how you would set up that equation. Questions? Okay. So in this example, C is at the center. So essentially we could think of it, if we extended it, it would be the diameter. So it's similar to the situation on the previous slide. We want to find the length of the radius. Now there currently isn't a radius drawn on this picture. Would you agree? There's part of a radius that's connecting to that AB chord right here. But let's actually draw in a radius right here. We want to figure out how long that segment is right there. So let's put an X there. That's what we're looking for. Ideas on what we could do? Yep.
A squared plus, oh, A squared plus B squared equals C squared plus B11 is divided by 2.
Yes, this 11 right here, which we learned on the previous slide, gets cut in half if there's a right angle from the center. So this right here is actually 5.5 on that right triangle. Which one is our C squared on that picture? The X, right? The hypotenuse. So we've got, I'm going to need some calculator help with this one, 30.25. So when we put those together, we've got 94.25. Final step, square rooting. 9 point something, what is it?
9.7. If you round it.
Okay. Questions on that? Okay, so that's using that property that that chord gets cut in half if there's a right angle from the center. Okay. We want to find the measure of AB. So let's think about this. We want to find out how many degrees this arc is. The measure of an arc, remember, is the same as the measure of the central angle. So if we figured out how big that angle was, then we would know the answer to this question, the measure of AB. Well, let's look at, there's a lot of numbers and writing on there, so I am going to redraw that triangle out here so we have some more space. This was 8, this was 5.5, and we figured out the hypotenuse was about 9.71. If we found this angle up here, what could we do to this number to get the answer? Yep, we would just double it. Okay, so if we're looking at this triangle, what are the two things we think of when we see a right triangle? What could we possibly use? Trigonometry or Pythagorean theorem, which we just used. Now, if we're looking for an angle measure, which one do you think would help us a little bit more? SOHCAHTOA. Yep, the trigonometry. So let's look at, we can pick any of the sides, but let's pick these two. And we're trying to find this. Let's refresh our memory on how to use SOHCAHTOA to do this. What two sides do we have? This one is the opposite side. This one is adjacent. So we look at our SOHCAHTOA. Which one has A and O in it? This last one, right? So that means we're going to use tangent. That's what T stands for. What always comes right here? The angle. We don't know the angle, right? So we put our variable there. Now tangent, the really nice thing about SOHCAHTOA, remember, is that it tells you what order to put your fraction in. So it says TOA, so we're going to do opposite over adjacent. So that would be over 8. Now normally with SOHCAHTOA, we automatically just start multiplying both sides by the whatever's in the denominator, okay? But in this situation where we're missing the angle, does anyone remember what different step we have to do on the calculator? Tangent -1. Remember those inverse tangent, inverse cosine, inverse sine? So what you're going to put in the calculator is tan -1, 5.5 divided by 8, and it's going to give us our angle measure. Can someone do that for me? Yep.
34.5.
So we just found this angle right here. Okay, but we needed to do what? We talked about this at the beginning of this problem. We need to double that. So what is the measure of AB? Okay, so we double that 34.5. Questions? Okay, SOHCAHTOA is not going away. We're going to use it in the next 2 chapters as well. So we'll get lots more practice. Okay, let's look at this one. We want to find that chord. That's where our X is. They told us the radius is 17. Now, the nice thing about a circle is you can swing that radius wherever you want to. Okay, so what if we moved it to right here? It's still 17, isn't it? Now we have some right triangles. So they told us this is 15. So the other one would be 15. Okay, remember, if you see a right angle symbol, then that chord got cut in half. So we know this is 15. Could we now find this segment? Pythagorean theorem. Which one is c squared? 17. So let's do that right here. We've got 15 squared plus, let's put a variable there, y squared equals 17 squared. This one's 225. What's this one?
289.
We subtract our 225 and we get,
64.
that works out nicely. What do we get for that little y value there?
8.
We got 8. All right, so let's put that on our picture. Now we know that this is 8. Okay, I'm going to use a different color. Let's swing the radius a little bit further to right here so that we're looking at another right triangle. I'm going to redraw that one out here because there's a lot of stuff going on in there. Okay, how long is this right here, the hypotenuse? That's the radius, right? Okay, so we swung that around. That was 17. How long is this one? So 13. If we look right here, we got 8. We just found that. And then this little chunk on the end here is 5. So we have 13 there. So now we have another right triangle where we could find a missing side. C squared is still 17. So we've got 13 squared, z squared, 17 squared. Solve for z squared. $120. So it's going to be really close to 11 when we square root that.
8.95.
Okay. Now let's figure out what we actually just found here. If we put this on our picture, it's just right here, right? We just found 10.95. Yeah, it got cut in half because it was a right angle there. So we learned on the first slide. So if this is 10.95, there's another equal segment over here, which means x would be 10.95 plus 10.95. Any questions on that? So use that radius to your advantage if you have a problem like this and swing it wherever you need it to go so that you can create those right triangles. All right, let's do the last page. We want to solve for x. Ready? All right, so these equal arcs mean what about this segment and this segment? They're also going to be equal. Okay, so we know those are equal to each other. And because those are equal, and this is going through the diameter, we know we have a right angle. Those are always all linked together, those properties. Now we don't have any just true radius lines drawn in, so let's do that. Let's draw a radius right here. You always want to connect it so that you create a right triangle. How big is this angle right here? Remember, the measure of an arc is the same as that central angle. Okay, now let's fill in a little bit more information without doing any solving or anything yet. Let's draw that line right there, that green one. Okay, on that red triangle, that smaller one that we drew, we didn't have any numbers other than the 57 and the x. But if we draw this green triangle, okay, notice we have 12 right here. We also have x on the bottom. And all we would need to figure out is how big is this angle? And then we have a SOHCAHTOA problem because we know this is 12, this is x, and we're just looking for this angle up here. Well, we can easily figure this out. What is the angle right next to 57? How did you get 123? Because they're on a straight line, they're supplementary. So this is 123. Okay. What do you know about this line and this line? Besides the fact that they're blue, what do you know about them? What vocab word would be linked to those two blue lines? What is it of the circle? They're both the radius, right? So are they the same length? Okay, so if we're looking at this triangle here, what kind of triangle is it? It is isosceles. We're using lots of previous information here. If it's isosceles, what do we know about these two angles? They're equal. So how would we figure out how big they are? This is 57. We're going to have to take 57 divided by 2. What's that? How much? 28.5? Okay. Well, we just figured out this angle right here, 28.5. So this is a little bit cleaner picture over here, 28.5 degrees. Let's talk through this SOHCAHTOA here. What two sides do we have? This is opposite, straight across from the angle. This is, which one are we using? Yes, another tangent problem. We have opposite and adjacent. So now we've got tan what? Yep, angle goes here. What order? Tells you the order right here. What do we do to both sides? We talked about this a few minutes ago. Multiply both sides by the denominator. We have x by itself, so we throw this in the calculator. What do we have? Questions? Okay, I walked you through the more difficult problems in the homework. They're not going to be this difficult, but just kind of refreshing your brain on a lot of things we've talked about so far this year. Okay, any questions?
Saturday,